Okay, so under Arrhenius' theory, what constitutes an acid?
An acid is something that creates an H plus ion and dissolves in water.
This is really hard to write on this. Increase H plus ion concentration in H2O. Okay, and a base?
That's where it makes a hydride ion waste of water.
Hydride? No,
No,
that's
it's
an H minus.
Hydroxide.
Hydroxide. Here we go. Brain fart.
Okay, so acid increases H plus concentration in water. Hydroxide is increased when you add a base to water. All right, how about Bronsted-Lowry acid?
A substance that donates a proton.
And a base? Yeah, sorry, Allison. No paying for the kits. All right, Lewis acid.
It's an electron receptor. Acceptor.
Sometimes people will write an accepts electrons to form a bond. Sometimes that gets written, so in case you run into that. And the base is obviously the opposite. All right, so what's wrong with Arrhenius that two more definitions need to be created?
H plus ions just can't float around in water.
Yeah. They
They
interact.
can't be aqueous.
Doesn't exist.
Anything else?
I think I once said was that not all acid-base reactions require water.
Okay.
They don't require a solvent or hydrogen.
Anything else? Water molecules just don't turn into H plus and OH minuses. You need two water molecules to run into each other to turn into hydronium ion and hydroxide. Why would Lewis name nitrogen atom a base?
Because I have it here. Nitrogen is capable of giving away electrons with bonds, so it's a Lewis base.
It has the
So those two electrons on the top of the nitrogen atom are going to, that lone pair of electrons is allowed to make bonds with stuff. So most of the base reactions happen in your body with nitrogen. All right, acetic acid is monoprotic. So I got H, C, H, H, C, double bond O, OH. So can you give me 2 reasons why this is the acid?
I thought it was because of the electronegativity of the oxygen.
All right, that's one. Bond is very polar. Can you give me another reason?
Is it the only one that can hydrogen bond?
Well, tell me about these 3. Go with this. Tell me
Is
about.
it because the oxygen can donate another pair of electrons to the carbon next to it, but none of those hydrogens on the other carbon can make any more bonds to satisfy that carbon?
No, the carbon can't make another bond to the oxygen.
Uh,
This carbon already has his allowable 1, 2, 3, 4 bonds. But this oxygen can take these electrons here and just add them to itself, and then this whole thing becomes acetate. So these 3 hydrogens over here, they're identical. Chemically, they're 100% identical to each other. So if I'm telling you that only one of these is going to be acidic, because I told you that because this is monoprotic, then it can't be any of these 3 on this side over here. Because if it was one of these, which one would it be? Man.
The one that's different. This one that's with the.
So the only one that's different is this one on this other side. So that's how you know that's the one that's acidic. And the real good reason though is that one is bonded to an oxygen, which has a high difference in electronegativity between the oxygen and the hydrogen. So it's very polar. So the hydrogen's electron that is used in sharing for that bond is mostly hanging out around the oxygen. So it doesn't have much control over it. Okay. I wanted you to write the condensed structural formula too. So CH3COOH. Alrighty. Describe how to make 750 milliliters of 0.2 molar hydrochloric acid starting with concentrated hydrochloric acid. So which equation are we doing here?
Polarity.
Easier?
I thought we used the dilution equation.
You use the dilution equation.
Illusion.
So
Illusion.
M1V1 equals M2V2, and the concentration of the concentrated hydrochloric acid is 12.1 molar, or I think your note said 12 molar, so whatever, times the volume of 1 is equal to 2 molar times 750 milliliters. So just solve for V1. 2 molar times 750 milliliters divided by 12.1 molar. Where's my 1500 divided by 12.1. So 124 milliliters of concentrated hydrochloric acid. So then you go through that whole process. Get a 750 milliliter vol flask. Add, I don't know. So this is a little bit different than we would typically do it simply because this is an acid. So I would say we would probably add about 500 milliliters of H2O. Jeff's here. Hey, Jeff. All right, so 500 milliliters of water, then add the 124 milliliters of con HCl. Why am I doing it this way? Why aren't I just throwing the 125 in and filling up to the line with water?
It will like boil, won't it? And like kind of bubble and flap.
Yeah. What are you supposed to always do?
Pour it down a glass
Yes.
to rod.
No, you're supposed to add the acid to the water, not the other way around. Because if it's a container of concentrated hydrochloric acid and you dribble water in there, the first drop of water is going to boil to the point where it's going to splatter the hydrochloric acid all over the place. Because it's just one drop of water that's being heated by 124 milliliters of hydrochloric acid, in essence. And the other way around is I've got 500 milliliters of water, and when the first drop of hydrochloric acid hits it, it's not like that one drop of hydrochloric acid is able to heat and boil that 500 milliliters of water that fast. So add the acid. So we kind of do it in multiple ways or we do it a water addition, then we do the hydrochloric acid addition, and then add water, H2O, near line, and then fill to line with dropper. Alrighty, if you add 10 milliliters of 5 molar nitric acid to 10 molars of 5 molar hydrochloric acid, which will be left in the container? Okay. So I've got HNO3 and I've got KOH. So what's going to happen when these two things get put into a container together?
You make water and
Whatever's left,
yeah.
which is a potassium and a nitrate. And this thing here is completely aqueous because it's a group 1 metal and potassium. That's water, it's a liquid. This guy is aqueous and this guy is aqueous. Okay, so what's in this container?
Open water.
There's 0 molar this left and 0 molar this left. What's over here?
Water and dissolved potassium nitrate.
Is it 5 molar?
5 molar. Yes.
Or is it 0.25 molar?
5 molar, wasn't it?
Yeah,
Doesn't change.
it doesn't?
Or it's all 5. It's all you add 5 molar. Same there.
Right?
10 molar?
It's now in 20 milliliters.
Hmm.
So tell me about the volume of my mixture. It's twice as much as my 2 starting products. So think about it this way. This nitrate right here was sitting in 10 milliliters of water and its concentration was 5 molar. But now it's sitting in 20 milliliters of water. So what's its concentration? Half of what it was to start with.
Okay.
The same thing with the potassium. We don't care about the molarity of water. What's the concentration of water in water?
Water.
Water. Don't care. So,
Much water.
okay. So lemon is sour. Why?
The citric acid in it.
The fruit has acids.
Yes.
And then the peel?
I don't know what the chemical's called, but it has some type of base in it.
Peel has bases. Okay. All right, that's all I got.
And we can just take pictures of this and put it into the Dropbox for the assignment, because I can't write on a PDF file from my computer.
You mean like when you did homework 1 and turned it in?
Yeah, I haven't turned it in yet because I wanted to ask you if you want me to take pictures of it and put it into the drop for the assignment.
There's no. I'm not sure exactly what you mean by Dropbox.
when I'm turning it in, I can't write on the PDF file and turn it in. I have to take a picture of my work from a writing book.
I get that, but what do you mean by Dropbox?
It's
The submit a file
Okay.
box.
All right, okay. Because you say Dropbox, and Dropbox is a thing, like
Yeah.
Google Drive or OneDrive or something like that. So I just wanted to be clear that we were talking about the submit section for the homework. Yeah. Okay. Yeah, that's totally fine. Photographs are fine. There are free software programs that let you write on, and you guys all have access to Microsoft Office 365. Did you know that?
It is now.
You're all members of the college, so it's part of your tuition. So if you've got, this is note 1. So if you've got note 1, just like a blank page open, you can just take any PDF that you've got. And so, all right, here's this homework that's a PDF, and just drop it and let go of it. And then blammo, there it is. And then you can go up to the draw section and then just start writing in it. But I guess that would mean you would need a pen, a way to write. I bought this thing for 20, or it was like 18 bucks. I don't know if you can see that very well. This thing right here. Amazon, I think it was $18.50 or something like that. Comes with a pen, and then it just allows you to, like, you guys can see my cursor moving around on top of that PDF, right? The homework.
Yeah.
So it just lets you write on it. So, I mean, if you feel like, I don't know, this might be something you'd want for now and for the future, since you might be doing a lot more Zooming. I guess I don't want this anymore. What are we doing? No. There it is. Okay. So what were we talking about? We stopped right here, right? We didn't actually get to
We
salts.
stopped at polypropic.
I don't think
we talked a little bit about salts.
I don't think we. No, we did. We totally did talk about salts.
Yeah,
Didn't we?
we talked about gypsum and that kind of stuff.
Yeah. Okay, we talked about salts. So polyprotic. Poly, many, protic, proton, so hydrogen. So when I'm looking at phosphoric acid, this is actually called a triprotic acid because those 3 red hydrogens are acidic, meaning they can all come off. And the phosphorous acid is a diprotic acid, meaning that 3rd hydrogen can't come off the phosphorus acid in an acidic format. Nitric acid only has 1 acid, so it's monoprotic. And carbonic acid has 2 H's, and they're both protic. Can somebody tell me what the theme here is to be an acidic hydrogen?
It looks like you're kind of attached to an oxygen.
Anything else?
You're sticking out away from kind of the rest of the molecule.
If you're a hydrogen attached to an oxygen, and that oxygen is attached to something that's doubly bonded to an oxygen, you're acidic. Because if this is HO, but the thing it's attached to is a carbon that's got 3 hydrogens on it, this is not an acid. This is methanol. This is an alcohol. So even though it looks the same, they both have OH groups. In this molecule, this acts as one object. And in this molecule, only the H acts as something. This section here acts as its own little entity. So this little, that's a grouping, making that H acidic. This is a grouping, making that H acidic. And this is a grouping making that H acidic. And so over here, I've got that H being acidic, and I've got that H being acidic, but this one doesn't have the oxygen connection, so it itself is not acidic. Same situation here. I got a hydrogen connected to an oxygen connected to something that's doubly bonded to an oxygen. And both of these hydrogens, they share the carbon doubly bonded to an oxygen, but it doesn't matter. Both those hydrogens are acidic. And we've talked about this before with strong acids and strong bases, and then weak acids and weak bases. So if I'm a strong acid, the arrow is one direction. It's going over to, in this case, hydronium ion and a chloride, and it doesn't go backwards. And the same thing with the sodium hydroxide. And then the hydrofluoric acid, on the other hand, since that's a weak acid, it's going to have a bidirectional arrow, meaning it's in equilibrium. So these are controlled by an equilibrium expression, in this case a Ka, or this one down here is the equilibrium expression for a base. So calcium hydroxide is a weak base. You're actually going to be using calcium hydroxide. It's in your lab kit. I just put all those lab kits together last night, and yeah, that was fun. Yay. So if you were to put calcium hydroxide into your mouth, it wouldn't burn because it's a weak base, which is why they make Tums these days out of calcium hydroxide. Suppose they act like it's also a calcium supplement when it's really not. It's not a very good way to absorb calcium into your body. It's actually kind of hard from a calcium hydroxide standpoint to do that. Okay, so I want to look at this. Everybody look at this little table here for a sec. And then we'll talk about what it means. So that it's got a Ka1, Ka2, and Ka3. What's going on here?
Looks like a hydrogen is being emitted
From the phosphoric acid?
yeah.
So it's not easy to pull that first H off of there because it's a or it's a weak acid. So it's not supposed to be easy. So the value is 6.92 times 10 to the negative third. So what's that ratio? It's 1 divided by 6.92 e negative 3. So for every one H that comes off, there are 144 phosphoric acids still sitting there. So it's a 1 in 144 of them detach. All right, so the first one's come off, and now instead of starting with phosphoric acid, I'm starting with dihydrogen phosphate. So now this guy's already missing an H, and I want to pull the second one off. So tell me about that, the difficulty of doing that.
It's a little bit more difficult.
A little?
I mean, oh yeah, the magnitude of magnitude a lot.
5 orders of magnitude more difficult. Why is that? Why is it 10,000 times harder to pull the next H off? The first H I pull off, I'm pulling it off of a neutral molecule, a molecule of no charge. The second H I'm trying to pull off, I'm trying to pull a positive off a negatively charged polyatomic ion. So something that's negatively charged doesn't want to give away things that are positive. So it's 10,000 plus times harder to do that. And then what about the last one? When I try to pull the third H off?
Extremely hard.
It's another Oh wait, the first time it was 100,000 times harder. This time it's 10,000 times harder than before. So
Yeah.
what's the difference between 10 to the negative third and 10 to the negative 12th? A billion. So it's a billion times harder to pull the third H off than it is to pull the first H off. So you'd need a strong base to pull that H off of there. Just one second. Penelope, where are you going?
Aw.
Sorry, my daughter's trying to run away.
Uh-oh.
Hey, go back. Get over there. You can stand right there next to them.
I am too. I want to go out of this house.
She's
I tried to run away when I was little, but I had a loaf of bread in a cart, and I brought it to my grandparents' house. They lived like right down the street.
You left your house with a loaf of bread and brought it to your grandparents' house?
Yeah, and I was also with a wagon, my favorite wagon when I was like 5.
Cool. Don't tell me stuff like that. Because we live on 35. I don't want her walking down the road with a wagon and a loaf of bread. We have 4 ducks that are like 6, 7 weeks old. Well, maybe they're older than that now. And she's trying to get them to go into the kiddie pool. And they're terrified of her. And she's mad. Okay. Let's yeah, she's tired of being quarantined. You're right. Let's talk about conjugation. Okay, so if you look up conjugation in the dictionary, it says 2 things that are joined together, especially in pairs, are having or operating as if joined. But they also have this other one where having features in common but opposite or inverse in some particular way. So the conjugation can either be things that are joined together, like a couple of people that are married, or people or they're opposites of each other. So a male and a female or something like that. So they have something in common, but they're still opposites of each other. Like a bolt and a nut. They're opposites of each other, but they like one is kind of useless without the other one. So this concept is being applied to chemistry in the way of weak acids and weak bases associated with their salts. Okay, so this is hydrofluoric acid. And so in this case, if it's going to react with water, the hydrofluoric acid is obviously going to be the acid since it's called an acid. And we know water can either be an acid or a base. So in this case, it's going to be the base. And then on the other side of the equation, since this is a reversible reaction because it's a weak acid, I have a conjugate acid and a conjugate base. All right, so what do I mean by that? Well, this is an acid. So what would Bronsted and Lowry say this acid is going to do?
It is going to Bronsted and Lowry.
Bronsted and Lowry.
It's going to donate protons.
It's going to give an H. Okay, great. So that's why it's called the acid. And so what's the water going to do?
It's going to accept it.
Accept that H. All right, great. So tell me about this thing right here. What could or what will this F minus do?
Try and gain a bond with something. Try
Yeah.
and gain the,
Bond to what?
which one?
Bond to a proton, right?
Yeah.
This reaction goes both directions. If it goes both directions, that means this fluoride is going to need to grab an H so it can turn back into fluoride on the other side. So what is this? It's going to act like a base because it's going to accept a proton. And what's this hydronium ion going to do? It's going to give away one of its H's, so it's going to act like an acid. And so then the water molecule is going to turn back, or the hydronium ion is going to turn back into water. The fluoride ion is going to turn back into hydrofluoric acid. So over here, the fluoride is a base, where over here it's an acid, and on this side it's an acid, where on this side the water's a base. So the acids and bases switch places. Well, this, I don't know, I want to say switch places. What I want to say, how about switch roles? So on this side, this thing is giving away, but over here, to get back to where it was before, it would have to accept. Where the water was perfectly able to accept a H here, but now over here, this thing cannot accept another H. There's no such thing as H4O plus 2. That thing doesn't exist. So the only thing it could do is give away the H that it had accepted. So then the fluoride accepts back that H and it turns back into hydrofluoric acid. That sound good? Does switching back and forth occur really quickly? Yes. But the flipping back and forth that occurs really quickly once it's reached equilibrium. So let's say 1,000,000 of these guys turn back into that. At equilibrium, what's happening? A million of these
They're going the opposite direction.
are
right?
going in the opposite direction. Exactly. So even though it's happening very fast, it's happening very fast both directions. Right? So let's think about you running lines on a basketball court versus, say, Usain Bolt running lines on a basketball court. Where do you end up when you're finished running lines? You haven't gone anywhere, right?
Way behind.
Well, you haven't gone anywhere. The two of you stop running and you're both standing in the same spot. Even though he ran a lot more than you did, you're still standing in the same spot. So same situation here. It doesn't matter how fast the reaction is going back and forth. The forward and backwards are going at the same rate. Otherwise, it wouldn't be in equilibrium. Is there a way to capture the ions and use them for something helpful? Morning, Annika. Use them for something helpful. Battery. That's usually what we use this in this situation, to make the bond with something they wouldn't normally bond with. I'm not sure what you mean by that. If it's in equilibrium, it has to go back to bond with the same thing it was bonded with before it broke apart. Otherwise, it's not an equilibrium reaction. Does that make
This wouldn't
sense?
happen to like strong acids or bases, right?
Wait, say that again?
This wouldn't happen to like a strong acid or a strong base.
No, it just goes in one direction. We don't
Okay.
really care about the teeny tiny reverse reaction. Okay, so water auto-ionizes. And remember I said we would talk about Arrhenius even though it's wrong?
Yeah.
All right, so this is Arrhenius, and it's wrong, but it makes this whole explanation easier. So suck it up. Otherwise, I could write a water molecule here and write 3O there, but it doesn't really matter. The end result is the same. Okay, so this is the equilibrium expression for water. And so where did the water go? Why do I have it X'd out on the bottom down there? What do these bracket thingies mean? Yeah, right. Kalina says it exactly. It's water's concentration in water. There's no molarity for water in water. It's 100%. It's water. So I can't put a concentration down there. Water isn't aqueous. It's the thing that makes stuff aqueous. So I just don't even include it. And another example for this would be, so something that's insoluble, like, I don't know, lead to sulfide, something like that. So this is a solid in water, but a teeny bit of it does dissolve. Most of it is this direction though. And so I've got this little bit of lead and this little bit of sulfide here, but the equilibrium expression is just the KSP concentration of Pb plus 2 times the concentration of sulfide minus 2. I don't write the lead, I can't write this down here, sorry. PBS, because it's a solid. So what's the concentration of solid lead 2 sulfide in lead 2 sulfide? It's 100%. So you can't put liquids or solids in an equilibrium expression because the equilibrium expression is talking about talking about concentrations of stuff. And the concentration of a liquid in a liquid is 100%. There's no concentration of that liquid inside that liquid. And the same thing with solids. If it's a solid, then the whole thing's a solid. Okay, so the K value for this is 10 to the minus 14th. So how much does this happen? How much does this happen in water?
Very, very rarely.
Since it's 10 to the minus 14th, it's a tiny number. Great.
Small.
So can you tell me what the concentrations are? So if I know that this, sorry, let me erase this for a sec. If I know that this equals 10 to the minus 14th, can you tell me what the concentration of H plus and the concentration of OH minus are? Yes, they're very small, but you can give me a number.
10 to the negative 7.
It's 10 to the negative 7th, right? Because what I know about this is the number of these and the number of these have to be equal to each other. Because when the water molecule breaks apart, I get an H plus and an OH minus. So over here, if this value is 10 to the minus 14th, and I know these two things are equal to each other, then it's 10 to the minus 7th times 10 to the minus 7th. Because exponents with the same base, when multiplied, are just added up. So I get 10 to the minus 14th. Does that make sense?
Yep.
Okay. So let's talk about pH. So let's look at 7. So we probably know that 7 is the pH of water that's pure or neutral. So here's my pH value here. And the kW of water stays the same this entire time. It doesn't change. It's the kW for water. So if I have it at neutral, then I've got 10 to the minus 7th OH minus and 10 to the minus 7th H plus. And we'll show why the pH number is actually 7, but it's 7, okay? So what happens if the water is a little acidic, meaning the water has a pH of 6? Why is this pH 6? What's changed?
There's more OH.
No,
More H.
there's more H. That's 10 to the negative 8 and 10 to the negative 6, right?
Oh,
So this number here is a decimal place in 5 zeros and then a 1. And this one here is a decimal place 7 zeros and a 1. So the OH is 100 times less concentrated than the H. So where's the pH number come from? The 7 or the 6th? It's right here.
Comes from the H plus.
It comes from the H plus. So this 5 and this 4, 3, 2, 1. I'm not sure if you knew you could have a 0 for pH. You can also have a -1 for pH. We'll show that here in a sec. So what do you notice about the math with this? What you should notice is every time I'm talking about this, let's say pH 3. So my H plus ion concentration is 10 to the negative 3rd. My Kw is 10 to the minus 14th, and it can't change. So how do you get 10 to the negative 3rd, and your answer has to be 10 to the negative 14th?
And the negative 11.
That's the only way. So these are easy when they're whole numbers. If I know that my pH is a 12, that's telling me that my H plus ion concentration is 10 to the minus 12. So I need a -2 for my OH minus, and that gets me to 12. Sorry, that gets me to my 14, which gets me to 12. So tell me about the concentration difference between How much more acidic is this than pure water?
100 times.
It's not.
10 times?
It's 10 times, right? Because
Yeah.
what's this number here in decimal format?
0.7 1
And then this number?
with 6. Yeah, with 6. By 1.
So 5 zeros and a 1 versus 6 zeros and a 1. So pH 6, my H plus ion concentration is 10 times more acidic. So what's the difference between pH numbers 2 and 3? 10.
10,
What's the difference between pH 2 and 4?
20?
20, 100.
100,
100.
yeah, 100.
So this scale, what would you call it? What type of scale is this?
Would it be exponential?
No.
Linear?
Yeah. No.
What's it called? It's not log, is it?
It's logarithmic.
It is log. Okay.
Hey, where are you going? Okay, come inside. Hurry up. Go around. Go through the front door. Okay, fine. Then right there. Hey, you gotta stay near mom. Okay, so this is a logarithmic scale. Can you guys think of another scale that's logarithmic?
What's the name of it?
I don't know. I asked you. Anybody? It measures scary things.
Scary things?
That's what I said.
What was it? The earthquake?
Earthquake.
Scale?
Earthquakes.
Magnitude scale, right?
The Richter scale
Richter.
measures earthquakes, and the scale itself is logarithmic. So if you're in an earthquake measure 4, and then somebody else is in an earthquake measuring 5, their earthquake was 10 times more powerful than yours. So
Don't you also use decibels?
decimals?
Decibels like sound.
Oh, is the decibel scale logarithmic? I don't
I
know.
believe so.
Okay. So you're saying that decibel 6 is 10 times more loud than decibel 5? I don't know about that.
Google.
Yeah, I don't think that's the case. Doesn't look like it.
That goes up by what's a 10?
It goes up by factors of 10. Well, this does. But threshold of human hearing and breathing, that's not 10 times. Maybe. Yeah, no, I don't think it's logarithmic. Sorry. Okay. So if they're talking about earthquakes that we have all the time in this area, they're usually in the 3 range, but not 4 range. And you might have felt very, very light tremors with high 4s, but there hasn't been a 5 here in a long time. We're really just hovering around somewhere in the 2s and somewhere in the low to mid 3s.
Where do those happen? Because I've never felt an earthquake here.
They happen all along the Cascade Range.
Yeah, we're right from fault.
Yeah, I know where.
If you
They're very powerful.
if you look up the Geological Association, U.S. Geological Association, and you type in a zip code, they'll tell you all the earthquakes that have been in your area, for as long as they've been doing it. So they'll tell you anything that happened yesterday, and it's every day that something's happening. It just might be a 1 or like a 2, and that's definitely not something you're going to feel.
We get a lot of them. They're just like barely. You can barely feel them unless you have what are they called?
Earthquakes?
There's earthquake scale.
Can you feel an
Richter.
earthquake that's at a level 1?
I don't think a regular person could.
You get them like a machine.
Um,
Since there's less activity because of the coronavirus, they've done a lot of good science.
oh, yeah, I can believe that for sure.
Ooh.
We can't hear you very well, but I understood what you said, Gene. When I worked at Benson High School in Portland, we did a job training at Washington High School in Portland, and Washington was closed to students because it wasn't earthquake safe. And we were in the basement doing a computer training when we had a 5.5. That we felt. And we had just been talking about why that school wasn't a school anymore for students when the whole building started to shake, and I was out of there in 4 seconds. Everyone was like, why did you just leave us? Like, what would you expect me to do? Hold the building up? Okay, so let's move on with this. Ka times Kb is always going to be equal to Kw. And H plus ion concentration and OH minus concentration are always going to be equal to Kw. So if H plus ion concentration goes up, what has to happen to hydroxide concentration?
It goes down.
Has to go down. They're absolutely inversely proportional to each other by orders of magnitude. If the H plus ion concentration goes up by an order of magnitude, so goes up by 10, the hydroxide ion concentration has to go down by 10. So now they're 100 away from each other. Okay, so let's talk about pH. The simple truth is chemists made pH so regular people wouldn't be anxious. I guess that's the best way to say it. That they wouldn't be upset or irritated or nervous about stuff. Okay, so whoa, that shouldn't have happened. I don't even know how that got. Oh, I see.
I had fun stuff today.
So if I told you that you needed to maintain the correct acid-base ratio in your swimming pool or your hot tub, and I said that you needed to make sure that it was 2.5 times 10 to the negative fourth hydronium ion concentration. How many people are not going to be happy with that?
The general population.
The general population hates exponents and doesn't even think that half people don't even think negative exponents is a thing. Like, no, that's not true. You can't put a negative sign there. Yeah,
Nice.
yeah, you can. But what if I said, all right, the pH of your hot tub needs to be 3.5?
And they'll be like, okay.
I just need this to say 3.5. Okay, I will add this stuff until this number says 3.5. So literally, this system of pH is just around because people who are scared of numbers needed something that they could accept.
Oh, that's sad.
So it's a mathematical construct created by chemists. So P, lowercase p, equals negative log of whatever I'm looking at.
Oh.
So if I have H plus ion concentration, and here I am using Arrhenius when it doesn't mean anything, and it's 10 to the negative sixth. So what happens if I take the log of 10 to the negative sixth? What's my answer? The 10 goes away, and then I get negative 6. And what happens if I multiply it by negative 1?
That's 6.
It turns into 6. So I got rid of a negative number, I got rid of an exponent, I got rid of a negative exponent. So I could give a person a decimal number that doesn't freak them out. Well, 1 second.
Or he's going, we can say whatever we want.
Joke's on all of you. None of you can understand or hear me.
What was that?
Sorry, I don't speak italics.
Yeah, you need to come back from the 90s, please.
You sound fine, guys. Sheen, say like, I don't know, say cows.
Cows. And
Oh
she
yeah, that
sells
was
she-
actually,
she
that was
sells
really
like
good, dude.
Yeah, cows.
It was like cows.
All right, I'm going to mute all of you because I don't know what you're talking about.
We're talking about cows.
And Sheen's awful mic.
Gotcha.
Horrible mic. Sheen, get a good pair of headphones.
Okay, so let's do
Potato.
something else here. Are you okay with this number?
Sure.
Ish. I mean, I can kind of get what it is, but also,
It's
Okay.
just a number. It doesn't matter that the exponent has a decimal place. It absolutely doesn't matter. Can somebody tell me if I told you that this was H plus ion concentration? What's the pH of this solution?
2.5.
It's just 2.35. That's it.
Yeah.
That's it.
A little bit
So-
of two.
If you said that this was this I'm supposed to get a concentration like this on my hot tub, people are going to freak out. There's no such thing as negative exponents, and you can't have decimal places with exponents. I've been told that in class.
You can't change my
And
mind.
I said, how did you get out of Math 95? So when it's actually in this format, it's even easier. When it's written as a decimal with a negative up here, because tell me what this number would be in regular scientific notation. So I've got 10 to the negative 2.35.
0.00, would it then be 235?
No, it is not, because it's a decimal exponent. You'd have to actually punch this into the calculator.
Yeah.
So you actually get to use 10 caret in this case. So 10 caret negative 2.35. And this thing equals 4.47 times 10 to the negative 3. Okay? We're all right with that?
Yep.
Okay, so let's do a little. We're gonna do some math because I feel like if I don't do this, then people do poorly. So all right, so I've got 1 times 10 to the negative 5th. What pH would that equal to if I'm talking about hydronium ion?
5.
5.
Mhm.
Okay, great. How about 1 times 10 to the negative 4?
4.
pH 4. Which one of those is more acidic?
4.
The 4 is more acidic. Okay, so just so we're clear on that. What about 5 times 10 to the negative 5? How about this? Can you give me a range
Range.
for the pH? Tell me what it can't be less than and tell me what it can't be more than.
It can't be more than 5. Or, yeah,
Less than 5?
less than.
halfway
less
between
than
4 and 5.
Except it's an exponent, so it's not actually halfway. Because this is a logarithmic scale. So 5 isn't halfway in between a logarithmic scale. So this isn't, the answer to this is not 4.5 is what I'm saying.
Yeah.
But can you tell me what it can't be less than?
4.
4. Can you tell me what it can't be more than?
5.
5. So can you tell me, give me the range that you will find this pH?
Between 4 and 5.
Between 4 and 5. Yes, just a second. All right. You can't be in this room. Out. Okay, so if you get, let's say, all right, let's just look at this number right here. We have the answer, but look at 8.3 times 10 to the negative ninth. Tell me what the range can be. So what you do is get rid of the 8.3. So what pH would that be?
9.
9. But it would be 9 if it was 1 times 10 to the negative ninth. But what we have is 8.3 times 10 to the negative ninth. So which one of these has more acid in it? The top one.
Top one.
It's a bigger number, right?
Yeah.
Okay, so what's happening to the acidity?
It's going up.
It's becoming more acidic. So what do I do with the pH number?
Lower.
Lower. So this equals pH 9, and this equals what? 8 point something or other, right?
Mhm.
You okay with that? But definitely not 7 point something or other, right? I know it's not 7 because why? So how about this? 9.99 times 10 to the negative ninth. What's that really, really close to?
10.
1 time, really close to 10, right? If this turns from 9.99 to 10, what does my number turn into? We okay with that?
Negative 9.
So we just changed the pH from 9 to 8. But right here, I'm not at 8 yet, not at 8.0. I'm at what? I don't know, 8.02, something like that. I haven't quite gotten there yet. So in this example problem here, I'm getting pretty close to the 10 value, right? Where this number goes from 10 to the negative ninth to 10 to the negative eighth. So then my pH should be pretty close to 8. Is it? It is. It's 8.08. It is pretty close to 8. So what I want you to be able to do is look at an H plus ion concentration in any kind of format and immediately be able to say, I know what that pH is, or I know what the maximum and minimum are for that pH to be able to give me a range. Does that make sense?
So a correct answer would be giving you a range.
If I was asking you approximately or something like that, you could say, I don't know, maybe like 8.1, somewhere closer to 8 than it is to 9, but I can't give you an exact number without a calculator or a slide rule. Anybody have a slide rule? Nobody owns. Come on, Sheen. I think you have a slide rule. No? Shocking.
Is the slide rule that thing with the like 4 like?
He does have a slide rule. I knew
I'm
it.
able to find one next to my dad's floppy disk.
And an abacus. Well, of course you have a computer.
Oh, an abacus. Wait, what's a slide rule? Oh,
Things.
Oh, well, that is just terrible resolution.
for some reason I was thinking a slide rule was an
Oh.
abacus.
This is a slide rule.
Oh, pixel.
So that thing around the outside, it slides back and forth, and then that is a ruler that's got 3 pieces, and the center piece slides. So you can figure out logs by using a slide rule. I haven't
Sick.
done it since middle school, so it's been a while, but it actually turns out to be really easy. It's super quick and requires no batteries.
That's not fun though.
I don't know. That looks kind of fun to me.
Okay.
Stick to the CI-84.
89. Actually, did you?
CI-98.
84.
I like the 84. I think
This
it's
is what I had during my undergrad and grad
That's
school.
disgusting. That thing is ugly.
True, but it did math that the other calculators can't do.
It looks easier to use.
You
But
installed Doom on your TI-89. That's pretty funny. The 92 can do a lot, and it's kind of fun. I had Tetris on mine. The year after I graduated from undergrad, they banned them though because somebody finally figured out how to put like your entire set of chemistry notes on it.
Does it come with a giant cover like the other calculators have?
It does. That's what this thing is around the backside.
Nice.
It's a side of a. It feels like a iPad Mini, but 5 times thicker.
I was thinking, like, how big compared to a hand is that thing?
It's the size of an iPad Mini,
Oh my god.
but again, 5 times thicker. Okay, so let's talk about the pH scale. Pure water is in the middle there, and then if I go to the left, urine has a range. Can anybody tell me why?
Depending on the person.
It's all about dehydration. It doesn't really have anything to do with what you eat unless you're talking about water being something that you eat. The more dehydrated you are, the more your pH changes. So usually the pH of urine, does anybody have any idea? Of a normally hydrated human? About 6.8, somewhere around there, really close to 7. It's really not very acidic in any way. Unless, again, you're dehydrated. Then what's the difference between dehydrated person urine and regular person urine?
It's smelly and yellow.
Urea in it.
They both have urea in it. Since we're talking about pH here, let's talk about pH.
It would be more acidic.
How much more acidic?
10 times, or depending on how hydrated the person is.
They're as
From
dehydrated
75
as they
to
can be and still be functioning. 100 times, right? The difference between 5 and 7, as far as the pH scale goes, is 100. So if you're super dehydrated and you go pee and you're like, damn, that burns. Does that make sense?
Oh man.
It's 100 times more acidic, so of course it's gonna hurt.
Burns. Oh my god.
Okay, so tomatoes,
Drink water.
just a little bit more acidic than your urine could possibly be. And then tell me about the difference in acidity between a tomato and an orange.
10 times.
The orange is approximately 10 times more acidic. How about like a Coca-Cola
To an orange?
to an
To a
orange?
tomato. To an orange. 10 times.
It's more than 10 times more acidic than an orange and 100 times more acidic than a tomato. And how much more acidic than pure water?
Oh jeez.
Freaking to the
100,000.
Give me a between.
1, 2, 3, 4.
10,
It's like
100, 1,000,
2,000.
10,000,
Oh yeah.
100,000. So it's between 10 and 100,000 times more acidic than water.
Oof.
So shotgunning a Coke, that's why it's painful.
Oh.
It's not even 10 times less acidic than puke. And you guys use this in lab the first 2 quarters several times. And so you're like 100 plus times more acidic the cola is than 1 molar hydrochloric acid. Let's go the other direction. So blood, 7.4. It needs to stay there. If it varies, you die. Baking soda in water, you're looking at a little over 8, which is why people use it to neutralize. Or if you have an upset stomach, too much stomach acid, you can drink something that's got baking soda in it and it'll make some CO2 and neutralize the acid. Seawater's range is based off of, what do you think?
Polluted air.
That was like the
Temperature.
temperature. Yeah, okay.
Because temperature controls CO2 with H2O, which makes carbonic acid.
Right.
So it is about carbonic acid, but it's a temp thing. Milk of magnesia, which is just magnesium hydroxide. You're up at 10.5. That's another something or other that's going to make your stomach feel better. And then something like ammonia that you would wash your windows with. That's much more basic, right?
Mm-hmm.
You're looking at 10, 100, 1,000, 10,000, between 10 and 100,000 times more basic than regular water is. and Drano is right here.
Ooh.
So yeah, it's
Can
very
you get
acidic.
past 14?
Say again.
Can you get past 14?
You can. So let's do past 14 and less than 0. So what do I need to do? I need to take the negative. I have H plus ion concentration. I take the negative log of the H plus ion concentration, and that gives me my pH. We okay with that?
Mm-hmm.
So what happens if I change? So this is my hydrogen ion concentration. In this case is 1 molar. So what number is that with scientific notation? It's 1 times 10 to the 0. So what pH is that?
0.
0. We okay with that?
Mhm.
So what if instead my pH is, or my concentration is 10 molar? Because we can have 12 molar. So what's that in scientific notation? The number 10. 1 times 10 to the first molar. Okay, great. So I've got 1 times 10 to the first. I take the log of that. So the log of 10 gives me what? 1. And then I multiply it by -1, and what's my answer? -1. So you can have pH -1. Sulfuric acid goes up to a concentration of 18 molar. So we can just do the math on that. So that's 1.8 times 10 to the first. So what does that work out to be? 1.8 E 1 negative, or sorry, I gotta scroll to it. I don't know why I'm not on it. See, I need a slide rule. I'd already be finished.
Where's she at?
Negative 1.3.
So the negative log of the number 18 is,
Sheen said negative 1.3. Oh, never
He's
mind.
wrong.
it's close, 1.25. So this is negative 1.25. So that's about as low as the pH can get, negative 1.25. I can't get it any lower than that because I can't get any more acid into the water. What happens when I try to put more of the sulfuric acid into the water?
Kind of vapor.
It vaporizes away as a gas. I've already saturated the water, so it can't be any more concentrated. So let's do the opposite. What if I have my pH is equal to, let's say, all right, let's say, okay, so first off, let's start here. What's the OH minus concentration here?
100%.
No. 10 to the negative 14th. What's the H plus ion concentration?
0. 10 to the 0.
We okay with that? 10 to the 0? So 10 to the 0 becomes what number? 1.
1.
1.
Yeah.
And so then there's 10 to the minus 14. So this is for a concentration of 1 molar. Well, what if my sodium hydroxide had a concentration of 10 molar? So this is 10 times more concentrated than this. So what's the pH going to be?
15.
15. pH is going to be equal to 15. So you can get about 1.4 molar sodium hydroxide. So it's going to be a number between 15 and 16. So 15 point something or other is as high as your pH can go. So it's not a 1 to 14 value. Okay. So here are some KAs for some strong acids and strong bases. They're, numbers greater than 1. So for all practical purposes, we're saying that the whole reaction goes one direction and there isn't an equilibrium going on here. But if you wanted to get technical, hydroiodic is the strongest of your acids. And the sodium all the group 1 metal hydroxides, they're all between 10 to the second and 10 to the third for their KBs. So again, we don't really care all that much. We just know that they fully disassociate because they're strong acids and strong bases.
Why is nitric at 20 instead of 10 to the something?
Because that's what its number is, 20. These values are for weak bases.
Yep.
So these are all KBs. Why does that say KB? Should be a capital K and a lowercase b, but whatever. What do all of these substances have in common? Aniline, ammonia, dimethylamine, ethylamine, glycerin.
They'll have some form of nitrogen.
They all have nitrogen in them, right? Those nitrogens are lone pairs of electrons on top of them. They all act like bases. So all of those bases are able to accept protons because of the nitrogen. So we've got all the bases there. Besides ammonia, do you guys recognize any of these?
Alanine.
It's an amino acid.
Glycine sounds pretty familiar.
Glycine is also an amino acid. Yep. How about methylamine? Do you know this one?
methylamine.
Does anybody know why methylamine might sound familiar?
Methamphetamine?
No.
Meth.
Daisy.
Baby food. Baby formula.
Methylamine.
Okay, so does anybody remember any scandal with baby formula?
It's gross.
No, scandal.
People don't like when mothers use baby formula when they're supposed to be feeding.
That's not really a scandal. Anything else?
Did they put something weird in it?
Like methylamine? Okay, so it looks like. Go ahead, Sheen.
Oh,
No? All right.
your portrait. There we go. So they did execute.
So when you let's say you were trying to make more money and you were trying to sell baby formula, what's something you could do?
Add something so that you have technically more.
Yeah, what does a bartender do when they're trying to stretch the alcohol?
Add water.
Like Sheen said, they cut it, or Kalina said they add water. Okay, so they were taking milk and they were diluting it down, but that will get caught. You can't just dilute it down. So what you need to do is fool the testing body that's making sure that there's enough, that's actually milk. So what these people figured out was that the testing body doesn't sample for proteins. The testing body samples for amine groups, which are in proteins. So if the amine group concentration, and we'll talk about what amines are at the end of this term, are high enough, then you obviously have enough protein in your milk. Well, this guy and this guy over here figured out, you know what? We're going to cut the milk with water, and then we're going to throw methylamine in because it's an amine, and so it'll look like protein. Turned out the amount of methylamine that these babies were getting, because that was all they were drinking, was milk that had methylamine in it. It was killing babies. So what's the number here? At least 6 kids died and 300,000 kids were made sick. And this is China. So what happens if you do something like that in China?
Yeah, executed.
They kill you. That wouldn't happen in the United States, right?
Nice.
Those executions happen
Trial.
with execution. You only get execution in the United States with something like
Murder.
capital murder, where you're 100% positive that this person was trying to kill that person. These guys weren't trying to kill anybody. They just ended up killing people. So in China, though, you did kill somebody, so you die. Unless you had enough money, Kalina, then you just get parole. Okay, so methylamine.
Home safety.
Methylamine was the thing that they were using to taint the formula. So for a long time, people were buying baby formula from people who lived in Hong Kong. Why Hong Kong and Singapore? Does anybody know why Hong Kong and Singapore were the places that Chinese people would buy their baby formula? Those two cities in mainland China get direct imports from the rest of the world because neither one of them were owned by the Chinese government for a long time. They are now. He's correct. They were not Chinese. Britain owned Hong Kong for it was either 100 or 99 years. I can't remember what it was. But regardless, it was literally British soil in Hong Kong. And so a lot of the trade stuff that happened after they gave up their rights to it were still in place. So you could be sure that the formula that you got came from California.
Nice.
So
Hong Kong.
Hong Kong with a C.
So
Yeah.
there was a huge black market for baby formula for a long time. And you might say to yourself, well, why don't you just breastfeed? You shouldn't be giving them baby formula anyway. What's the argument back?
You can't always.
Not everybody can breastfeed.
Like,
Can you give me some reasons?
One of my cousins, she got cancer and had to have her breast removed, and she had a baby.
There you go. You don't have breasts. There's a way. Any other way?
Single dad.
Yeah, mom died during birth. Now there's
Yeah.
somebody
Or
to
you
give.
just don't want to. It's your choice.
Sure. Yeah, absolutely. I mean, you do what you want, but you always are at the risk of what is somebody putting in this baby formula. And,
Yeah.
and in China, it was methylamine. Okay, so these are weak acids. So there are a lot of wet nurses. Yeah, we don't have that wet nurse booming industry. Does anybody, first off, everybody knows what a wet nurse is? If you don't,
Yeah.
it's a woman you can hand your baby to and they'll nurse them for you because they're currently nursing their own babies. Or maybe they were nursing a baby and they don't have a baby anymore, but they keep nursing other people's babies, so they keep producing milk. So a wet nurse was something that was in Western society for a long time and kind of, I don't know, went out of favor. People started thinking it was gross or something like that. I'm not really sure what the situation was.
You gotta feed your baby somehow.
Children were actually healthier when they got passed around the village. Can anybody tell me why?
Guessing it's all the different, because when babies get, antibodies and that.
Yeah, so you get antibodies. Your mom was sick with something, and you have the immune system of your mother by drinking the milk. And then you get passed off to another mother who had different illnesses, and now you get her antibodies. So it's not something that happens now, but when there were small villages and there'd be, 10 babies drinking milk, they just literally sit in a circle and pass the babies around because they knew that when they did that, their kids didn't die. They stayed healthier. And you're probably not going to see that like go into a Starbucks and women are passing their babies around to each other. Probably not going to happen anymore, although it would be smart. As long as you trusted the other person not to be sick with something, those babies would have better immune systems right out of the gate.
And people can barely breastfeed in public anyway.
Well, it's 100% legal in every state except for Idaho.
In Idaho.
I'm not joking about that. You can be issued a misdemeanor citation for breastfeeding in public, but in every other state in the United States, it is illegal to even confront a woman who's breastfeeding. So go at it, all of you women with infants.
With infants.
All right, so let's back down here. So there are lots of weak bases, but there are a lot more weak acids and a lot more useful weak acids that we deal with. So here's acetic acid, here's vitamin C, boric acid. You guys get that in like the boric products. Butanoic acid, that's actually pretty gross. Carbonic acid, I love that. Gage hates it. Chromic acids, toxic. Citric acid, oranges, lemons, and whatnot. Formic acid, fire ants, love fire ants. Heptanoic and hexanoic acids, those are just acids that are hydrocarbon acids. Then hydrofluoric acid, we'll talk a little bit more about that later. Obviously, lactic acid, nitrous acid.
Painful.
You probably oxalic acid. You probably don't know that, but we found it first in ox. Phosphoric acid. You guys know that one. Sulfuric number 2, not sulfuric number 1, and then uric acid. So lots of ones we know. So let's talk about I've got an acid. I've got a formula. I've got a Ka. So the Ka is the amount of dissociation. So if I'm looking at ascorbic acid 1 and ascorbic acid 2, does it make sense that ascorbic acid 2's Ka is a lot smaller than ascorbic acid 1? So what I did is I'm pulling this H off of the vitamin C. And if I want to pull the second H off, it's harder because this thing is negatively charged. So it's 7 orders of magnitude harder to pull that thing off of there. So let's look at a couple of different acids. Okay, so let's look at heptanoic and hexanoic. Which one of these is a stronger acid? They're super close, but which one's stronger?
Hexanoic?
Hexanoic acid's a bigger number. I know there's a
Yeah.
10 to the negative fifth there, but it's 1.14 versus 1.29. So that means more of the H's in hexanoic acid are able to come off than the heptanoic acid at the same concentrations. Okay, now what's this number over here? What's this lowercase p?
The negative log.
It's this negative log thing. So in the same way that we did the negative log of the H plus ion concentration to get pH, I'll take the negative log of the Ka to get a number that's quicker to write. There really is no other reason to do it. If acetic acid's Ka is 1.74 times 10 to the negative fifth, my pKa is 4.76. It literally is just easier to write. How do I go from this number back to this number? So how did I go this way? I did the negative and then took the log, right? So I take 4.76, I make it negative 4.76, and then what do I do with the negative 4.76? I make it the exponent
Of a log.
of a 10. I can leave it like that, or I can figure out what its scientific notation number is, which is 1.74 times 10 to the negative fifth. Since those numbers are equal to each other, you can use either one and it doesn't matter. What else could I write? I could write 0.0000174. If you wanted to write any of those numbers, you're more than welcome to because they are identical. You cannot be faulted for writing any one of those. Unless the person specifically says, give it to me in scientific notation. Okay. Changes. What?
Okay.
All right. We have time. Just do one more thing on this, and then we'll stop for the day. Okay, so pH changes from ionic compounds. So tell me another name for an ionic compound.
A salt?
It's a salt.
Salt.
So can you change the pH with salts? You must, because we're going to talk about it. What
Yeah.
happens if I put NaCl solid into water? You get what?
NaNCO, Na plus CO negative.
Mango.
Do you get any pH change?
Would it become more basic?
Why?
I don't know. It's a guess.
Mango? What?
I said I don't know. It's a guess.
He was reading the chat window. The answer for table salt is no. Nothing happens. But that's not always the case. The reason it doesn't happen is when a sodium ion interacts with a water molecule, nothing happens. This does not happen. Can anybody tell me why this doesn't happen?
Because if that happened, we'd all probably die.
Okay, can anybody give me another reason? Sodium ions are soluble. Okay?
Yes.
So why would the sodium form this in water? The answer is it can't and it won't. So sodiums cannot change the pH. All right, so what about the chlorides? Interacting with a water molecule. So what could happen?
Well, wouldn't it change the pH? Because that's, I mean, we talked about hot tubs with pools. You gotta maintain the pH of your pool.
It's got nothing to do with this. I'm talking about chlorides.
So
this chloride here, this reaction cannot happen. Can somebody tell me why?
Because the chlorine is soluble, isn't it?
This is
It's a strong acid.
that's a strong acid, and what does that mean?
It's gonna be dissolved.
It dissolves in water. So if I put this in water, would this yank the water molecule apart to turn back into this just to dissolve again?
No.
No. So why does table salt not affect pH? Because this thing, if this was a base, it would be NaOH. And that doesn't stay connected in water because it's soluble. And if this was an acid, it'd be HCl. And that doesn't stay connected in water, so it will stay disconnected, meaning it can't pull a water molecule apart. All right? So what about this? What if these two things interact with each other?
Oh, they're gonna make hydrofluoric.
They're going to make hydrofluoric acid. Why?
It's a weak acid. It doesn't want to.
It wants to be stuck together. It doesn't want to let go. So if I get it to let go and I have a fluoride floating around, when it runs into a water molecule, it's like, I want that H back. And what's left behind? So tell me what happens to the pH.
Going to, let's see what is that. It's going to increase.
It goes up by a lot. Okay? So how did I get this to happen? Well, if I put NaF into water, it would happen. Why? Because the sodium says bye-bye, leaving behind myself a fluoride, which then says, give me an H, which gives me this, which leaves me with that. So I put this salt, NaF, into water, and the pH does what? It goes up. So salts can affect pH. So think about that for next class, and then we'll talk about that some more. Does anybody have anything they want to talk about? Anyone? Anything interesting going on?
I'm eating eggs.
I said interesting.
It's very interesting. They're boiled.
Wait, with ketchup?
No, they're plain. No salt, no pepper.
Man, you ketchup with eggs. It's delicious.
No, there's so much sugar in ketchup.
I have to mute you two because that's disgusting. You're free from living in your basement? Why would you want to be free from living in your basement?
And it's nice and damp and cold,
Ew.
moist.
I was outside for like 3 hours yesterday, just sitting on my front lawn because I needed the sun so much.
Whenever I think of somebody stuck in a basement, I think of Silence of the Lambs.
Right?
Oh, oh wait, never mind. Oh yeah, no, I have a question.
So if you're in that basement and somebody throws a bottle of lotion down, you should try to get out of the basement.
I was gonna ask, where are we in Hood River? Are we getting the lab kits?
Anybody want to tell her since she was napping while we were talking about it?
Listen, okay.
Tuesday and Thursday in Hood River. Sorry, Monday and Wednesday in Hood River, 5 to 6. Just pull up to the front door, and somebody will be standing there, a ways away from you, with a stack of boxes for you to pick one.
Sick, I'll be away from you.
Or you could go to the Dalles if you want. 10 to
No,
12 Monday or
no.
Tuesday.
I hate the Dells.
Who doesn't?
You, boo.
Okay, if there aren't any other legitimate questions, I will. I'm going to end this.
I will not.